As you see, I'm going to use a blackboard rather than the usual way that people give talks now. I'm an old-fashioned guy, and I will use the blackboard for my talk. It's indeed a pleasure to be here and to speak to this audience. I will talk today about a reformulation, a time-symmetric reformulation of quantum mechanics. In this reformulation, we discuss every quantum system with two vectors instead of one. One vector coming from information about the system in the past, and another vector coming back from the future from information gained about the system in the future. As you will see, since this is a reformulation, it will give, of course, as it should, the same prediction as ordinary formulation of quantum mechanics, but it has a number of important advantages. The first advantage is that it reveals a host of new phenomena associated with quantum systems that are pre- and post-selected. These are very interesting new phenomena that has many interesting experimental consequences, and I will discuss some of them today. Another important advantage is that this approach suggests a generalization, and also a generalization of quantum mechanics that will solve in a very simple way the famous measurement problem. And I will discuss this also in my talk today. So let us begin by discussing the following problem. In classical physics, we know that if we define the state of a classical system at a given time, and we know the Hamiltonian that acts on the system, there is no possible surprise in the future. This classical theory is completely deterministic, and nothing in the future can reveal anything more about the system than was known about it in the past. But in quantum mechanics, we know that the most important new feature of it is that it's non-deterministic. That means that we can start with two identical systems and nevertheless get different answers to a given experiment in the future. So the interesting question is, perhaps quantum mechanics is trying to tell us that from the beginning there was a difference between the two systems, but we can reveal this difference and find it only in the future. And that was the guiding principle in trying to develop this new approach. It started in the middle of 1960, where I had this idea, and I came to Peter Bergman and Joe Leibovich, that were my colleagues at Yeshiva, and told them, let us try to develop quantum mechanics with this idea that there is a difference between two quantum systems that are exactly the same, but this difference is revealed only in the future. And then we reformulated along this line something that's called now the ABL formalism, Aharonov, Bergman, and Leibovich. So here's how it goes. Suppose this is time, and at time t1, we find the quantum system at the state psi1. And then at a later time, t2, we find the same state, the same system at the state psi2. The question we ask now, what can we say about properties of this single system that was pre-selected and post-selected at some time in the middle, at some intermediate time? So suppose we consider a measurement in the middle time of some observable A that has a complete set of eigenfunctions, alpha n, such that alpha n is possible eigenvalues or possible results in an experiment. Our question is, what is the probability to find one of those given the condition that it started at psi1 and ended at psi2? That means that we do this experiment on all particles that started with the same state, record the results for all of them, but then discard all the results that we got when we did not find psi2 in the end. So we keep only the results in the middle for systems that started at psi1 and ended at psi2. So let's see how the conventional way of calculating this is, we say the following. Psi1 evolves in time until the intermediate time t. Then we make a measurement and find one of these states. So this was psi1 of t. From now on, we will have the particular result that we found, which is alpha n of t, which evolves now from this intermediate time until the final time, and then we postulate and find psi2 there. So the calculation is well known, how to do it. We take the original psi1, involve it in time from the original time t1 to the time t with the time evolution operator. If the Hamiltonian is not depending explicitly on time, u is equal to e to the minus I ht over h bar. Then we evolve it until the intermediate time, and we post-select alpha, and we select alpha n. This gives us an amplitude to start with psi1 at t1 and find the state alpha n at time t. Then we start with this state, alpha n, which we assume now that from now on the system is described by alpha n, propagate it from the intermediate time to the final time, and then post-select it on the state psi2. If we call this Cn, define this to be Cn, Cn absolute value square tells us what is the probability to start with psi1, get in the middle alpha n, and get at the end psi2. That is very straightforward. Everybody knows how to do that. Now we do a very simple mathematical change that mathematically is trivial. We simply take the u and bring it here, and we have now u daga psi2, alpha n, u psi1. Okay, this gives us exactly the same Cl. So we are allowed to do the calculation for the properties of the system in the time in between using this formulation, because it gives us exactly the same results as this one. Although mathematically these two are completely trivially connected, physically this is a very, very different picture, because what this picture tells us is that we can calculate the result of things in the middle by taking these two vectors on equal footing. What this formalism tells us, if we are interested in knowing something about the system in between, we should take this vector and propagate it forward in time. We should take this vector, propagate it backwards in time, because u daga is the operator going in the opposite direction of time. As you see, if I take u daga, I have to change t to minus t here. And we say that the property of the system in the time in between is given by these two information. This is something that can never be done classically, because classically, once this is fixed, there is no freedom to fix something else here. But quantum mechanically, it opens for us the possibility of saying that a particle, quantum particle at a given time t, knows not only what happened to it in the past, but knows also what is going to happen to it in the future. Now, this is a very dramatic change, because this says something unbelievable. How could the particle, this present, know already what's going to be happening in the future? Suppose I have free will. I can change my mind later what I'm going to do in the future, and still these particles already knows in quotation mark, what is going to happen. The reason why this is consistent, as I will show, is because of the uncertainty principle. If I could do an experiment here that will tell me already now what is this vector, then it will be against causality, because I can change my mind and send a different vector. As you will see, the prediction of quantum mechanics using these two vectors is such that it preserves causality in a very non-trivial way. So if you ask the question, why does God play dice, instead of saying like Einstein, God doesn't play dice, the answer is that God plays dice. Namely, there are uncertainty to allow a new possibility that the future is relevant for the present just as much as the past. This is a very starting point. Okay, so let us now begin to see what are the new implications of this way to look at quantum mechanics. Let us take the simplest quantum system that we know about, which is a spin-half particle. And we assume also that components of the spins are constant of the motion, no magnetic field. So we start with this particle with the state sigma x equals to +1 at the beginning. We found it by experiment. This was the time t1. And at time t2, we find the same particle with the state sigma y equals to +1. Okay, now the usual picture tells us that from here to here, the particle has only one property, which is sigma x equals to +1. The new picture tells us that, in fact, this particle in the middle has two properties. It has the property given by the vector coming from the past, which is sigma x equals to +1, but it also has the property of the vector coming from the future that tells us that the same particle also has sigma y equals to +1. The question is, can we find any experiment that will show us that indeed in the middle, both sigma x and sigma y were equal to +1? Which experiment can we do? Well, suppose we try to measure sigma x or sigma y. Then it's trivial. If we measure sigma x, of course we will get +1 because we started with it. If we measure sigma y, we know we have half a probability to get +1, half a probability to get -1, but we decide to throw away all the cases that sigma y is equal to -1, then it's not surprised that we'll find that only sigma y equals to +1 because we threw away all the others. It doesn't say that really the particle has sigma y equals to +1. So that's not the way to find it. So when I was thinking about it, I asked myself, what will happen if I will measure sigma x plus sigma y? If sigma x is equal to 1 and sigma y is equal to 1, perhaps if I do the experiment to measure sigma x plus sigma y, I will get the answer to 1 plus 1 is 2. But the minute I thought about it, I realized that is impossible, because if I divide it by square root of 2, that is just a spin component in the 45 degrees in the xy plane that can never be equal to square root of 2. It can be equal to 1 or -1, but never square root of 2. So what shall we do? It looks as if I was led astray by this picture. But I did not give up my hope, and I told myself, what is going on here? I know that if I try to measure this operator, I must use a magnetic field, inhomogeneous magnetic field like Stern-Gerlach, in the 45 degrees. This inhomogeneous magnetic field will rotate, precess around the spin, and it will change in an uncertain way both vectors. So the thing that I'm trying to measure destroys exactly what I'm trying to see. So I was trying to think, well, how can I save the day? And then it occurred to me that if I will think of a new kind of experiment that will interact only very, very weakly with this particle, then perhaps it will not disturb the two vectors and I will see something new. So that led to the idea of what's called now weak measurement. Weak measurement reveals a very surprising thing about quantum mechanics. We usually think that the more information we get, the more disturbance we might have. But it turns out that there is a very interesting limit in quantum mechanics, that if I'm willing to get very little information from each experiment, call this information epsilon amount of information, which is of the order of 1/n. So each particle gives me information of the order of 1/n. I have to repeat this experiment n times on similar cases to gain a finite amount of information. The beauty is that the disturbance of each one of the particles goes, in that case, like epsilon squared, 1/n squared. So I have now a limit where I have a large number of particles, all of them have the same state. I can find exactly all the information about this state without disturbing even a single particle, provided I have enough of them. It's a safety in big numbers. So let me just prove that and that will be the only mathematics I will do. And the rest of the talk, since I don't have much time, will be just stories, okay? But one piece of mathematics. So, suppose I have an ensemble of particles. All of them have the same state. For concrete example, suppose somebody prepared n spin half particles. All of them are pointing in the same direction, but he did not tell me in which direction it is. My task is find in what direction are they pointing. The usual procedure to do it would be the following. I will choose, I have enough of them, I will choose a part of them, a subgroup of them, and measure on all of them sigma x. I will get some of them plus, some of them minus. From this, I will calculate the average of sigma x if I have enough of them. Then I will do for another group the same thing for sigma y, the third group for sigma z, although I don't need that one much. And in this way, I will find the direction. But this is a very destructive experiment. Lots and lots of collapses happen there. Is there a way to find the direction of these spins without even disturbing one of them? Not changing the state of even one of them? The answer is yes. If there are enough of them, it's possible to do that. So we now have a way to observe properties of quantum systems without disturbing, without collapse, provided we have enough replicas. So how do we do that? We have an ensemble, psi, which is a product for n particles, for n quantum system. All of them are described by the same state psi n. And now I want to give you first, before I continue, an interesting result that I'm always surprised that I don't find it in any book in quantum mechanics. If I look in any Hilbert space, on a Hermitian operator A, X with it on a given vector in this Hilbert space, I know that I can always write it as A1 times psi plus A2 times orthogonal state to psi. This is a trivial geometrical effect. A times psi gives me a new vector. This new vector has one component parallel to original vector, and another component orthogonal to it. What is A1 and what is A2? It's very surprising how beautiful those things are, although they are connected with a single particle. And the answer is the following. I will tell you the answer. A1 is equal to the average of A, the so-called average of A, although we now calculate just for a single particle. And A2 is equal to the uncertainty of A. To prove it, how many of you have seen this in any book in quantum mechanics, this theorem? You have seen it. In which book?
It's not in a quantum mechanics book, but I give this as an example in my course.
Okay, good. And you did not hear it from me?
Sorry?
You did not hear it from me?
I think you mentioned it in your quantum paradoxes book.
Ah, okay. All right. Let me prove it to you because it's such a beautiful theorem and it should be in any quantum mechanics book. How do I find A1? I simply multiply by psi. So I have here psi, A psi, which is the so-called average of A, although we talk now just about a single system. And on this side, I have A1 times psi psi, which is 1, and A2 doesn't contribute because psi is orthogonal psi to this state, okay? So A1 is the average of A. How do I find what is A2? I multiply the vector by itself. I multiply the vector A psi by the vector A psi. On this side, when I multiply, I can bring the A here, because it's Hermitian, so this will be psi A squared psi, but that is what's called the average of A squared. On this side, when I take the scalar product of this by itself, I get A1 squared plus A2 squared. So I see that therefore A2 squared is equal to the average of the square minus the square of the average, so it's delta A squared. So this is a very beautiful theorem that I'm going to use now. But I want to emphasize that you should all remember the theorem. This is a beautiful theorem, general theorem, that any operator times any vector is equal to the so-called average of A times the vector plus the uncertainty of A times some orthogonal vector. And this is true theorem in any Hilbert space. I'm going to use now this theorem in my calculation. So what I do now, I look at an operator A total, which acts on the whole ensemble. A total is defined to be the sum of the individual A divided by N. And I apply this to the ensemble. So what happens when I take a particular A here and act on the ensemble, a particular AM? It affects only the particle psi m. And how does it affect the particle psi m? According to the theorem here, it will live in the same state with A average and go to an orthogonal state with delta A, right? So therefore, if I look at AM multiplied by the ensemble, the state of the ensemble, this is equal to A average, the individual average to psi total, plus a state that I will call, it will be delta A, times the state I will call psi total M, where this state is the state where all the particles were left unchanged, but the mth particle went to an orthogonal state. So therefore, if I look now at A total, which is this, times the ensemble, all of this will contribute exactly the same value, and therefore the n will cancel. So this will be equal to A average, the individual average, times psi total, plus delta psi, some change. And it's trivial to show that delta psi times delta psi goes to 0 as 1 over n, because all these states are orthogonal to each other. So I have n orthogonal states. I take the square of them, they contribute n, and it's divided by n squared. So delta psi goes to 0 when n is sufficiently large. So therefore, it means that if I have an ensemble, I can measure any operator like this and find the average of this operator. So in particular, for example, if all the particles are described by the same wave function psi of x, and I look at an operator which is the sum of the projection operators on a given position for all the particles divided by n, I can do this measurement without disturbing any of the particles and find the average of pi n. But the average of pi n is simply psi star psi at this location. Since I can do any number of these experiments, if n is sufficiently large, I can find the state of any system, provided I have enough replicas without making any single collapse. So this is the beauty of weak measurements. Okay. Now, I come to the first big surprise. If I look at the operator on the definition of the average, which is psi times A psi, I can do now a trivial modification of this by writing psi and introduce here a complete set of vectors, orthogonal vectors, phi n, times A psi. If I sum over n, this is a unit operator, so I can always include it in the system. And then I can divide and multiply by phi n psi, and we get now the following: psi times phi n times psi, n times this peculiar quantity, phi n A psi divided by phi n psi. So I see that I can think about the A average in an ensemble as coming from a sub-ensembles, because this probability here is the probability to start with psi and getting a particular phi n at the end. Since my measurement in the middle doesn't disturb any of the psi, I was able here to divide the whole ensemble of initial psi into sub-ensembles according to the post-selection, and each one of them contributes to the same experiment with this peculiar quantity. Each one of them gives that quantity if I had the pre and post-selection. So I named this quantity weak value. The weak value of A is defined when I have pre and post selection as psi times as psi. Sorry, as phi n. The final state phi times the operator A times psi divided by phi psi. So I claim that this quantity describes a new physical property of a quantum particle between initial and final states. If the initial state is phi, and the psi, and the final state is phi, and A is any physical observable, this quantity describes how this physical observable will behave in all respects, provided the interaction with the system is very weak, doesn't disturb the system. So, for example, if I look at a spin-half particles, look at its Z component, and find that the weak value is equal to 100. That's the original article that I published in collaboration with two of my colleagues, Lev Weidman and David Albert. We say there, suppose we find that sigma Z weak is equal to 100 because we did pre and post selection on the two vectors that gave us this weak value. You see, because the denominator over here can be very small, we can get something that is much bigger than any of the eigenvalues. What does it mean that this is equal to 100? It means something very, very interesting. It means that this particle at the time in between behaves as if indeed it's a magnetic moment 100 times bigger than the usual one, provided we do only measurements on it that don't disturb it, weak measurements. So, for example, if I have this pre and post selected single magnetic moment in empty space, and which I have done in vacuum, I've done only the pre and post selection, found that in the middle it had 100. That means now that if I look at any place and look at the magnetic field produced by this particle, it will be 100 times bigger than the usual magnetic field. Infinite number of things, provided that the interaction between it and the electromagnetic field is weak. And we know that that is weak because we know that we can do experiments. For example, Newton, we can separate the Newton into going this way or that way. The magnetic moment here will produce a different field than the magnetic moment here if these two different fields were observable above the vacuum fluctuation. This will destroy the interference picture. The interference picture is not destroyed. That means that we can think about all the points, all the degrees of freedom of the electromagnetic field everywhere in space as being weak measurement of what is the property of this magnetic moment. Okay, I have very little time now, so I will start to tell you stories, okay? Without proofs. You're invited to read all the articles in order to get the proofs for all my stories. Okay. The first story is what we call the three-box paradox. I have a three-box, or three cavities. I know that I prepared an electron, a single electron, in a superposition, it's saying the ground state here, plus the ground state here, plus the ground state here, 1 over square root of 3 times psi 1 plus psi 2 plus psi 3. This was my initial state. I assume that this electron is free apart from, it's a free electron apart from the walls of the cavities. This is the time t1. At time t2, I make another measurement, and I find the state psi 1 plus psi 2 minus psi 3. Okay? Because this state is not orthogonal to that, I can find it. I ask now, what can I say about the electron in the time in between? And then something very funny happened. If I were to open in the time in between this box and ask is the electron there or not, I will be sure to find it there, because if I did not find it there, that state coming from the past would be orthogonal to this state coming back from the future, therefore I get 0. So it must mean that if I open this box, for sure, the electron will be there. But if instead I were to open this box in the middle, I again will find the electron there for sure, because this state coming from the past is orthogonal to this state coming from the future. So what's going on here? There is just one electron, is it clear? And also here, and what's happening in the third box? Well, in the third box, if I look at the weak value of the projection operator on this box, I get the value -1. So if I look now at weak values that I'm allowed to measure, the weak value for the projection operator here is 1, the weak value of the projection here is 1, the weak value of the projection here is -1. What does it mean? Some people like to talk about it as negative probability. I hate this idea, because probability has to do with counting. I can never count a negative number of particles. But if I ask myself, how would I make a measurement, a weak measurement, to find this, I realize that the weak measurement I can do is to measure, for example, the electric field outside. Measure the electric field that comes from here. Measure the electric field that comes from here. Then it turns out that because this measurement will be weak, I will find that the electric field coming from here, as if there is a single electron here. There is electric field coming from here, as if there is a single electron here. There is electric field here coming in the opposite direction, as if there is a particle with the opposite charge here. And it turns out that when you get projection operator, weak value of projection operator that have negative values, it means that the particles that are in there, as long as you measure them weakly, have all the opposite properties of normal particles. Not only will they have the opposite charge, but they will also have the opposite mass. The gravitational field they will produce here will be the same as the gravitational field of a negative mass. This is weak values, and you can check it experimentally if you can do the experiment. There are many experiments now that are done to measure weak values, not this one. Okay, the next story. Next story will be nice for people that read the book Alice in Wonderland. How many people read this book here? Alice in Wonderland. I hope most of you read it. I recommend it very highly. It was a book that was written many, many years ago, but apparently the writer there knew about quantum mechanics. Otherwise, I can't explain how he wrote it. So the story in this book is, all the book is about a girl by the name of Alice that goes in a dream to visit some wonderland. And in this wonderland, she meets lots and lots of interesting characters. One of them is a cat. Of course, all these characters can talk freely to her. So this cat is talking to Wonderland, to Alice, and by the way, the cat is from a place called Cheshire in England. That's why she called it Cheshire cat. So this Cheshire cat talks to Alice, and suddenly the cat gets angry and decides to disappear. But it disappears in a very funny way. First, the tail disappears, then the body disappears, then the face disappears, and the only thing that's left is a smile. So Alice says to herself, I have seen many times a cat without a smile, but what on earth is it, a smile without a cat? And of course, everybody that read this book before quantum mechanics saw that this is stupid. But now it turns out that quantum mechanics tells us exactly how to separate a smile from a cat. We will do it on a cat. It's enough that Schrödinger killed many cats. So we will do it not on a cat, but we will do it, for example, on a particle like a photon or a neutron. And we can arrange an experiment by pre- and post-selection that will have each photon, for example, goes from information in the past, we know that each photon goes with equal probability here and here. But when we do the right post-selection, we found out that when we succeed in this post-selection, the electron will go this way. Its energy will go here. Every property of it will go here, apart from the polarization in a given direction that goes by itself here. So it gets separated from the photon, like the smile is separated from the cat. We can do the same idea. I say we can, I never do experiments, but experiments can do it. We can take a neutron and send the spin one way, and the mass of the neutron, all its other properties will go the other way. Okay, that's story number 2. How much time do I have still?
10 minutes. 10 minutes.
Okay, 10 more stories.
Yes.
No, really only two, okay? All right, the third story. There is a very famous, very, very deep mathematical theorem. This is called the pigeonhole theorem. It's unbelievably deep theorem. What does it say? That if you have two holes and you have three or more pigeons, at least two of them or more must be in one hole. Unbelievably difficult to understand, right? Why should mathematicians even think of calling it a deep theorem? Why it's so trivial? Obviously, if I have three pigeons and only two holes, in one hole there must be two pigeons. Impossible otherwise, right? But quantum mechanics tells us that it's possible. In fact, we have now the thing that we call the quantum pigeonhole theorem that says the following. I have two cavities and three or more particles. I can arrange by pre and post selection a situation that if I will make weak measurement, no two particles will be in the same box. So, for example, I can even have particles, and I say that at least half of them must be together, so if they interact when they are together, there should be interaction that's proportional to n squared over 4. No interactions at all. When we do the pre and post selection, measure the energy of the system in between, or do other experiments, we see that no two particles were in the same thing. Again, beautiful new possibilities of properties of quantum systems that have no classical analog. So I can have more and more interesting stories, but now we come to something that I think is very close to the spirit of this meeting. And that's I want to show you how you can introduce a new approach to the measurement problem that is suggested by this, which is very, very simple and practically a natural generalization of quantum mechanics. What is the idea? The idea is the following. Look again what we said about our particle. Our particle starts as a shape psi1, but because later an experiment will find it in the shape psi2, already now the particle knows that it has, I like to call it a destiny state. There is a history state that is produced by this, and there is a destiny state that starts to live from here that knows where it's supposed to be ending. So suppose we take this picture seriously. What does it say? It in fact tries to tell us there is a new kind of hidden variable. The hidden variable is the state that already exists now. It's going to tell us what will be the result in the experiments later, but we can't detect it now because of the noise. So it's a hidden variable, but it's a new kind of hidden variable. Bohm's hidden variable is supposed to tell you the answer to any possible experiment. This hidden variable is supposed to tell us only the results of the experiment, the single experiment that will actually be done. And what does it mean? Remember that when Bell wrote his analysis of the EPR, he said, if each particle, when it goes out, each pair, when it goes out from the preparation, will know in which direction we are going to measure them, there will be no non-locality because it will be just a classical correlation. Only because we have to answer for all possible experiments, we get the Bell inequalities. So now, quantum mechanics tells us, no, if you take this picture seriously, each time we prepare the EPR, these two vectors that come out for the subparticles already know in which direction the experiments are going to be done in the future. Why did not Bell like this possibility? Because it says it's against the idea of free will. If we have free will, the particles don't have any business now to know which experiments we are going to do in the future. Now, I want to show, and that will be the last thing I will say, how I learned to understand 5 minutes. Okay. So, I try to understand how is it possible that these particles know what I'm going to do in the future, and nevertheless I'm still free to do whatever I like in the future. It seems to be a contradiction. So to solve this contradiction, I play the following toy game. I assume that I have two big laboratories in which there are people, etc., but each one of them is perfectly closed. In one of them, I arrange the initial condition at some given time to be such that the entropy is going in this direction. That means the natural time in which the entropy is going this way. in the other laboratory, I have also people, etc., but this laboratory was prepared in such a way that the natural time for it is going in the other direction. As long as they don't interact with each other and don't interact with anything else in space, this is a consistent picture. Now, I assume that I want to introduce the concept of free will. So I will say there is some guy here that I call a free agent that has the possibility at any given time to do something that is not predicted by the past. The important thing is that the thing that we'll do will affect the system only in the future, not in the past. That's the definition of free will. I can come at any time and change something in the system, but that effect will go only towards the future. So I have a free agent like this here, I have a free agent like this here. If he does something, actually it affects only that future. So far, everything is completely consistent. Now, I read one more thing. I read that this observer here would like to give some information to this one without disturbing anything. The way that we'll do it, he will, for example, put here some kind of static thing that he can either put it or not. Important is that once it's there, it's static, it's not moving, so there is no information in time. And this guy can send the photon from here, and it will be reflected from here, and there will be absolutely no effects on this system. So there will be a way to observe here, from here to here, something provided that is very carefully done, that observation does not change anything about the system, it does not make it unstable. So now we have the following situation. We have a situation that this guy has a free will either to put it later or not. Suppose he decides at some time here to put this thing here. This guy looks at it, gets the information back, and therefore, at the present here, even before that guy made up his mind whether to put it or not, he already knows that this guy has put it there. So far, there is no inconsistency in it. The only inconsistency will come when this guy will communicate with this one and tell him, look, you're going to do this, but he's free, he can change his mind. So as long as this is not allowed, the fact that this guy comes from the future and knows what he's doing doesn't mean that this guy is not free, because he was free from his past to make the decision any time that he likes here. The fact that this guy comes from the future and knows it, as long as he doesn't tell it to him, that's completely free. I coined the phrase, you can always be free from your past. You can never be free from your future. So the quantum particle that comes from here back and knows already what I'm going to do, but he's not allowed to tell me that because of the quantum uncertainties, it's the same thing as this guy that comes from the future. He knows already now what I'm going to do in my future, but it doesn't mean that I was not free. He came from the future, so he knows already what I decided after my freedom X. So, you know that there was always a big problem with the question of free will, my last sentence, that there is a saying that that the future is known, but permission is given. This was something that in Hebrew there is a very nice way to say it. But all wise people and all religious people are always worried. How is it possible that God knows everything what we are going to do, and nevertheless he punishes us because apparently we're supposed to be free? How can we be free if he knows what we are going to do? So the answer is, knowledge of the future doesn't mean that we are not free, because we can only be free from the past and not free from the future. Thank you very much.